Hello, this is Dr. Armand. Today we're going to be talking or discussing electronegativity, bond polarity, and nonpolar molecules, and look at a few examples of polar and nonpolar molecules. So sit back, relax, and enjoy the chemistry. So this is part 4 in this lecture series on Lewis structures, and we have to introduce one more periodic trend, which is called electronegativity. Electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. And so as you can imagine, as you go from left to right, it increases. So nonmetals have a better tendency to pull electrons towards them versus metals, and it decreases down a group. So fluorine is the most electronegative element on the periodic table. You should remember that. Followed by oxygen and chlorine are close second, and oxygen is second, and then nitrogen and chlorine come in around third. So the further you are from fluorine, the less electronegative you're going to be, aka the less negative you are. So fluorine is the most negative element on the periodic table. That's why fluorine always likes to have a -1 charge. Whereas francium, on the other hand, is the least electronegative element. We refer to it as electropositive. And so when we're looking at a bond, we're going to be looking at the difference in electronegativity to describe what type of bond it is. But again, as you go from left to right, electronegativity increases. As you go down a group, electronegativity decreases. So fluorine, again, is the most electronegative element. And so electronegativity helps us to distinguish between polar and nonpolar covalent bonds. So a nonpolar covalent bond is when there's equal sharing of electron density between the two atoms. And it's denoted with something that looks like this. And the key thing is shared equally between two atoms. Nonpolar covalent bond. And this is determined by the difference in electronegativity between the two atoms in the bond. If it's less than or equal to 0.4, is classified as a nonpolar covalent bond. You could think of it as two people playing tug of war, and they're both the same size. So they're pulling equally on the rope. And so atoms bound to themselves like an HH bond or a Cl-Cl bond are nonpolar because the difference in electronegativity is 0. But a very common nonpolar bond is not two homonuclear atoms, is the CH bond. CH bond has a difference of 0.4. The CH bond is a nonpolar bond. Another one is this carbon-sulfur bond. This is also a nonpolar bond because the electronegativity difference is 0. And so all homonuclear diatomic molecules must be nonpolar. These are things like H2, Cl2, O2, F2, I2, Br2, N2. I think that's all of them. So all of these are nonpolar molecules because they all contain nonpolar bonds. So that's one type of covalent bond, is a nonpolar covalent bond where you have electrons are shared equally between two atoms. And the way we determine that is based on the electronegativity difference between the two atoms. If it's less than or equal to 0.4, it's categorized as a nonpolar bond. So what you have to remember here is that you need to take the difference between the two atoms in the bond. So don't worry, you don't have to memorize electronegativity values. They'll be given to you on an exam, whatnot. You just have to remember that the difference is equal to or less than 0.4, it's nonpolar. The second type of bond is a polar covalent bond. So here, though, electrons are shared unequally between two atoms. This is like if you have a small person and a very large person playing tug of war. The large person pulls the rope closer to them. And the way you know if it's a polar covalent bond is if the difference in electronegativity is between roughly 0.5 and 1.9. The greater the difference, the more polar. So something that has electronegativity difference of 1.8 is more polar than a bond that has electronegativity difference of, say, 0.7. And what happens is we generate what are called partially charged atoms. So they get a partial charge. The one with the greater electronegativity gets the slightly negative charge. The one with the less electronegativity gives the slightly positive charge. And this charge separation results in what's called a dipole. And this is the symbol of a dipole here. Dipole always points toward the more electronegative element. So for example, if we have the bond CF, F is more electronegative than carbon, and this is a polar bond, so the dipole points towards the fluorine. The electronegativity difference, and it doesn't, you just take the absolute value. So 4 minus 2.5 equals 1.5. And so carbon-fluorine bond is a polar covalent bond. Now if we looked at something like HF, so F is more electronegative than hydrogen. If we look at the difference in electronegativity, 4 minus 2.1 equals 1.9. So then the dipole would point this way. So these are polar covalent bonds. Now, if you have an electronegativity difference greater than 1.9, this is referred to as an ionic bond where you have full charged ions. So one is a cation and one is an anion. And these are held together through electrostatic attraction between a metal usually and a non-metal. And so that's how you know if it's an ionic bond, is if the electronegativity difference is greater than 1.9. So now let's look to see how this applies if we look at a series of bonds. So here we have a series of bonds where carbon is the same and we have different other atoms attached to it. We want to know which one is the most polar bond. And remember from the periodic table, we got to know the trends of electronegativity. And so it increases from left to right and increases up a group. So again, fluorine is the most electronegative element. So the closer you are to fluorine, the more electronegative you are. Now remember that noble gases do not have electronegativity except xenon, but it's all the way down here. And so we want to look, so it increases this way, electronegativity. And it increases this way up a group as well. So we want to look to see which element is the closest to fluorine. That's going to be the one with the greatest difference. It's going to be the one with the most electronegativity, hence the greatest difference in electronegativity, aka the most polar bond. So we can go ahead and already negate C because C is with a noble gas and there's no bonds made with neon. The only one was xenon at the bottom. And so we got nitrogen, sulfur, bromine, oxygen, phosphorus. We want to look to see which one of these is the closest to fluorine. That's going to tell us which one's going to be the most electronegative. And so next to fluorine, we have oxygen. So oxygen is the most electronegative element out of all of these listed. So that means that the CO bond is going to be the most polar bond from the bonds listed here. So it has going to have the greatest difference in electronegativity because oxygen out of the ones listed has the greatest electronegativity. So now we're going to get into molecules. So we talked about bonds, polar, nonpolar bonds. Now we're going to talk about polar, nonpolar molecules. So a nonpolar molecule has one of two criteria. It can contain only nonpolar bonds. So if a molecule only contains nonpolar bonds, it's nonpolar molecule, or it contains polar bonds in which the bond dipoles cancel each other out. So for example, CO2, the CO bond is polar and the bond dipoles point toward both the oxygens. Now if we overlap these dipoles, we'll see that they cancel each other out. So this means that CO2 is a nonpolar molecule because the dipoles on the polar bonds cancel each other out. Next we have CH4, and CH4 can be two reasons why it is nonpolar. The first reason is it contains only nonpolar bonds, so therefore nonpolar molecule. So molecules that just contain carbon and hydrogen are nonpolar. So any molecule that just contains carbon and hydrogen is a nonpolar molecule. But now if we want to look at the dipoles, well, carbon is the more electronegative, so they all point towards the carbon, and then they're all going to cancel each other out. And so this would be also a nonpolar molecule. So again, the two criteria for nonpolar molecules, they all contain all nonpolar bonds, such as in CH4, or contains polar bonds in which the bond dipoles cancel out. Now, polar molecules, on the other hand, has to have two requirements. The first one is it must have at least one polar bond or one lone pair of electrons. So again, to be polar molecule, you got to have at least one polar bond and one lone pair of electrons. And the polar bond must be arranged so that the bond dipoles do not cancel out. The opposite of what it was for a nonpolar molecule. So for a polar molecule, the bond dipoles can cancel. And if there's two or more lone pairs of electrons on the central atom, they must be arranged so that their polarities do not cancel. So we have to have an overall net dipole in the molecule. So this means there is an overall net dipole in molecule. So let's look at H2O. We know from H2O that the OH bond is a polar bond. And then we have lone pairs on the oxygen. They're also negative. So if we overlap these dipoles, you see that we get a net negative. So this is the net negative region. This is the net positive region. So there's a dipole on the molecule pointing this way. So therefore, water is a polar molecule. Now if we look at ammonia, The NH bond is a polar bond. Nitrogen is more electronegative than hydrogen. They all point towards the nitrogen, and then there's a lone pair that has a little negativity. So when we overlap these, you see they don't cancel out. What we get is a negative end toward the nitrogen's lone pair and a positive end toward the hydrogen. So again, there's a net dipole in this direction. So therefore it's polar. So on water, this is the negative end and this is the positive end. On nitrogen, this is the negative end. Let me undo that. And this is the positive end. So this is a polar molecule. It has to have a negative and positive end, so it has a overall dipole. Now, what I'm about to show you next is a little bit of a shortcut based on the molecular geometry. But pay attention here because there's very specific requirements in order to do this. But this is a shortcut for doing polarity based on molecular geometry. Now, for this to work, all the terminal elements have to be the same atom. So that means all the X's have to live in Texas. They can't be different. So as long as the X's are the same on the outside, this will work. So the ones I'm going to highlight in orange are non-polar geometries, as long as all the X's are the same. So that is linear is non-polar, trigonal planar. So these are ones without lone pairs. Tetrahedral, trigonal bipyramidal, linear, octahedral, square planar, and linear. So these 8 geometries that I've highlighted in orange are non-polar geometries when all the X's are the same. And so as you can see, all the geometries with no lone pairs are non-polar. And then all the geometries labeled linear are non-polar. The only oddball is square planar because the 2 lone pairs cancel each other out. It's non-polar as well. So if you remember these will tell you which ones are non-polar. Now, one other thing is in organic compounds, you have what are called isomers, which are compounds that have the same formula but different chemical and physical properties. And these are called geometric isomers. So geometric isomers, we have a trans and cis. And so trans means that the same atoms are on opposite sides of the double bonds. This is a chlorine, it's on the opposite side of the other side of the double bond. So this is trans. And trans compounds are nonpolar because the dipoles cancel. So again, the chlorines are on opposite sides, one's up, one's down. That's trans. The dipoles cancel, it's nonpolar. Now with cis, as you can see, the chlorine atoms are on the same side. Since these are the more electronegative element, you get a negative charge on this end and a positive charge on this end. So you get a net dipole in this direction. So this is a polar molecule. And notice the difference in boiling point. So when you have comparable same size molecules, the polar one's going to be boiling at a higher temperature than the non-polar. So polar molecule compared to its non-polar counterpart is going to have a higher boiling point. And this is trans and cis. So trans is always non-polar, Cis is always polar. So we have IF3. We want to determine the polarity of this molecule. So the first step, determine the molecular geometry. So it has 1, 2, 3, 4, 5 pairs of electrons around the central atom. So 5 pairs of electrons, where 3 are bonds, bonding pairs, and 2 are lone pairs. So from this, we have to determine the geometry. And here the geometry is the molecular geometry. That's what we're interested in. Is T-shape, because again the bonds form a T-shape. So if we look, the bonds form a T-shape. All right. So now we know it's T-shape. We got to remember, was T-shape one of the ones that was nonpolar? The answer is no. It's polar. So this means that IF3 is a polar molecule. So that's the answer. So the bond dipoles do not cancel out. IF3 is a polar molecule. Now we want to look at SEF2. Let me draw that one. So SE. Again, it's very important you know how to draw the Lewis structures, because then you can identify the right geometry and the right polarity. So here we have SEF2. It has 4 electron pairs on the central atom, 2 lone pairs, and 2 bonding pairs. So you got to know what geometry has 2 lone pairs and 2 bonding pairs. The molecular geometry is bent. So we got to ask ourselves, is bent geometry polar? Is bent geometry nonpolar? Let me move it over here. Over here. Over here. Over here. Yeah. Is bent nonpolar? The answer is no. It's polar. So the bond dipoles do not cancel. So SEF2 is a polar molecule. Next we look at PF5. PF5 is this molecule. And so PF5, around the central atom, there are 5 electron pairs. And these are all bonding pairs of electrons. So these are 5 bonding pairs of electrons. So the molecular geometry is trigonal bipyramidal. So is trigonal bipyramidal nonpolar? The answer is yes. So you check back at that chart. And another key indication that PF5 is nonpolar is that there's no lone electrons on the central atom. Again, there's no lone electrons on the central atom. This is a good indication that it is nonpolar. And all the terminal atoms are fluorines. So PF5 is a nonpolar nonpolar molecule. And then lastly, we have SF4. Whose structure looks like this. So there are 5 electron pairs, 4 bonding pairs, and 1 lone pair. Molecular geometry, so you check geometry, which geometry has 4 bonding pairs, 1 lone pair. This is seesaw. And again, seesaw the bonds form what looks like a seesaw. Then you got to ask yourself the question, seesaw geometry nonpolar? Was it one of the ones I listed on the previous slide? The answer is no, it's polar. And again, it has that 1 lone electron pairs on the central atom, so it's a good indication it's going to be polar. So this is a polar molecule. So again, electronegativity is key because it can help us classify bonds as polar, nonpolar, and ionic based on the difference in electronegativity. You do need to know the trends for electronegativity. However, you do not need to memorize the values. They will be given to you if you need them. Secondly, nonpolar molecules either have to contain all nonpolar bonds, which is what molecules made up of only carbon and hydrogen have, or they have to have polar bonds in which the bond dipoles cancel. And the example we used was CO2. Or PF5 would be another example. Polar molecules have to have either at least 1 polar bond or 1 lone pair of electrons. The second requirement is that the polar bonds dipoles do not cancel, such as in H2O, or the lone pairs of electrons, their polarities do not cancel. And so from that, we talked about that if all the terminal atoms on a molecule are the same, then we gave you the list of geometries that were nonpolar. And those contained the geometries that were only had non-pairs, only had bonding pairs of electrons on the central atom. And then the other linear geometries and square planar, those were the nonpolar geometries. So I strongly recommend that you watch this video more than once. The first time, watch it, take notes. The second time or third time, watch it again. Try to work out the problems by pausing the video, working it out. And that way you can feel more confident in understanding the material. And so that concludes today's lecture on polarity and polar nonpolar molecules. If you learned something new or liked the video, make sure to press the like button. On that note, Dr. Armand is signing off. Until next time.